they're just about ready to continue. I don't think we heard that on here. She says, go to execute.
Copy. Ceci, go ahead and execute. Executing.
Enter go to enable.
Copy, go to enable. Nothing else.
And what they'll see now in their telemetry is they might see a disturbance on the entire observatory of these launch blocks actually coming apart. The entire observatory might just as like when you unlock your vehicle, you can hear the click of the door unlock. There's almost like a little vibe in the whole structure that comes through that we can. Sometimes we can pick up in other telemetry.
And I see I can verify to go to ARM.
That these fully release.
Copy, go.
In fact, I know the design of these actuators was specifically done so that they don't jar the telescope very much. They're actually very gentle.
Yes.
But even just that little bit of vibration could be detected.
I confirm armed. We're waiting on the stored command sequence.
And the stored command sequence is we don't ever want to break a command between the time we tell it to fire and
all stations. Our next go will fire ordnance OTE LRM Group 7. OC, your go to fire.
Copy, go to fire. See, you have to go to fire.
You hear the music.
I believe the music you're hearing, that's real. That's in the control room. They're
definitely in the control room. I actually hear it twice because I have my earphone on and then I hear it through here. So I had a hard time figuring out if you could really hear it, if it was just me for a second.
Yeah, that's right. Just obviously an air of excitement, and certainly, everybody is a little bit, their nerves are, on edge, but lots of optimism, lots of excitement, and lots of smiles. So that's it's an emotional moment for all of us.
Everyone's been working on this since the day of launch. Our launch deployments started with our very first one that was caught by the rocket itself as it floated. JWST floated away from it, the upper stage, and it's been nonstop day after day since then. Having each deployment come along in series, everyone has gone very well.
This is step ops on ops. I can confirm safe and disabled, and we're ready to continue with 693.031.
Copy that.
This is the step to actually do the
fire. The command line looks good. This is for OTE LRM Group 8, and you are going to execute.
Copy. You have to go to execute. Execute.
And you're going to continue.
Copy, go to continue. You have to go.
There's a total of 4 mechanisms that do the launch lock. 2 are at the hinge where which is actually closest to us in the display. At the joints, 1 at the top, 1 at the bottom, and then 2 kind of hold the wing back to keep it from rattling during launch, and are at the far corners of the side mirrors.
You're good to arm.
Copy, go. You have to go to arm.
I can confirm armed, waiting for the stored command sequence enable.
The thing that's so amazing to me is that what's happening today is the end of 178 release mechanisms. Every single one had to work.
Okay, all stations, our next go. We'll fire OTE LRM Group 8. OC, you are go to fire.
Roger. To C, you have the go to fire. Copy that.
Yeah, there was a lot of work to put into these. A lot of people have heard about our single point failures. Each one of these itself was a single point failure. In other words, if one of those 4 launch releases does not release it, we're not able to move this side of the mirror forward into position. So this would be our last of these 4 single point failures. There's still other single point failures and some that stay with us for the life of the mission. Different areas of structure or a mechanism. If the mechanism fails, we don't have a second path of light to bring the light down. But these are major milestones in getting the observatory into its final configuration.
For those of you who are joining us, you're looking at live coverage of the commissioning of the James Webb Space Telescope. Today we are unfolding the second of the wings of the primary mirrors. Joining me is Julie Van Kampen. She is the Deputy Commissioning Engineer. You can see people there excited and happy.
Bomb copies. Thanks, Step Lead. Glad to have the plot so we could follow along, share your enthusiasm. That's awesome. 178 out of 178. Congratulations. Thanks.
They just fired.
It confirms that all of those mechanisms fired, 178 of them. Over the course of the
This is Step Ops on Ops. I see that rock has completed. We're ready to continue with 693.032 DEU to standby.
Copy that.
And they can see indications in
And the
telemetry
command line looks good. You're going to execute.
Copy to C, you
that
have
everything
the go
is
to
successful.
execute.
And you're going to continue.
Copy go. You have the go to continue.
The next couple steps are going to be getting the deployment motors ready again. So before they checked them out, they had to put them into a standby mode while they were doing the firing. That was the safe configuration that you heard the deployment lead speak to. Now they're going to get them back into the configuration, and then they'll get ready to do their first small move.
OC, I can confirm we're in standby round robin. We're ready for 693.033 to restore default torque limits. The command line looks good. You're go to execute.
Copy. You have the go to execute. Executing.
And you're go to continue.
Copy go to continue.
And earlier we had mentioned the position called MOM. That's the Mission Operations Manager. And the elbow we're seeing in the top screen, that's Carl Starr. He's the MOM of JWST. When they do the small mirror move, the small motor move on the mirror here, in our tool that we get to see on the screen, the OVT, the Observatory Visualization Tool, we don't actually, it's such a small move, we won't see the tool actually change at all. It won't be until the major move before we can actually see it on this tool. And it looks like they're calculating that's going to be another 20 or more minutes until we actually see the full move take place.
Right. We're sitting here now. We're actually watching the Mission Operation Manager, and you'll also be seeing live coverage from the MOC, the Mission Operations Center at the Space Telescope Science Institute in Baltimore, Maryland. I'm there as well, although in an isolated conference room, so I can speak to you unmasked. Of course, we're operating under COVID protocols, which has made a challenge, but it's a happy and festive day here, and we're really looking forward to this next deployment. Later on in the program, we'll have a chance to take some of your questions from social media, and today we're asking you to use the hashtag #UnfoldTheUniverse. So hashtag #UnfoldTheUniverse. We'll be stopping our commentary as we hear commands. So, we may have a conversation, but then we'll stop to hear how the commands are progressing. As first, they make a very small movement to make sure the wing is moving correctly and all the motors are functioning correctly. And then in about 20 minutes from now, you will see on the left-hand side of your screen, you will actually see the wing click into place. And then after that, there will be a couple hours of latching it, of making sure that this is fully in its extended, permanent configuration. I see Julie's got a big smile on her face, which I love to see, because it's a lot of work.
So
up at the top there,
again,
Bill Oakes. Yeah.
Yeah.
Bill Oakes is the program manager, and you'll see him throughout this. As Julie said, he's sort of the head of the mission. Everybody kind of reports to him at this point. There's an interesting teamwork between scientists and engineers on a mission like this. And actually, Julie and I were talking about this earlier, that, I come from the background of being an astrophysicist. And when I think about Webb, I mainly think of all of the incredible data and the questions, the scientific questions that I'm looking forward to being able to explore with the telescope. Julie has a very different perspective. Julie, tell us a bit about your position as the deputy commissioning engineer. Tell us about what that job entails.
Sure. As the deputy commissioning engineer, I've worked to try to make sure all of the various pieces that it takes to commission the telescope come together in a way that makes an engineering sense. So there's a lot of people who have worked many, many years to make sure that it comes together operationally, working with how the commands are sent, how the control is done of the observatory, making sure our communications with DSN is worked out and timed with all of our activities. But I deal with the engineering aspect of that to make sure that if things are happening in a faster sense, that will still be safe. Like our operations can be handled 2 days earlier or 2 days later, should the timeline move one way or another from a hardware perspective. So many people are very interested in how the science will work, but I'm interested in how the parts of the telescope work themselves to make sure that they work together to actually give you that science.
Thank you. And that's the question, of course, about how you become an engineer or how you become a scientist. What is your background? I mean, what do you have a degree in, for example, that led you to this particular job?
My actual degree, both my undergraduate and I have a master's degree in mechanical engineering. And basically, I started off being interested in how to design and build things. As a kid, I liked to build forts. You name it, I like to put it together. So I went to school to be a mechanical engineer, graduated from school. My first company was a small company, so you kind of got to do a little bit of everything. So you kind of learned to be the Jill of all trades. And from that, I moved to NASA and got into the testing department and was able to do actually a lot of the Hubble servicing missions from the testing side to get those instruments and components that were being sent to Hubble on the different servicing missions ready for those missions. Then eventually I moved over to JWST, and I've been on JWST since 2003. And I've been a systems engineer on the instruments and then the payload and now onto the commissioning.
Wonderful. So we will pause our commentary when we see your commands from the Mission Operations Center, but we do have time to take a few questions on social media. So whenever people ask questions like this, I'm touching wood right now. It says Nicholas on Twitter asks, would the observatory still be operational if one or a few of the mirrors break? Is there anything out there that could break them? So, I mean, so that there's maybe a couple of different ways to answer this. I mean, what happens? All of the mirrors can be aimed independently. What happens if, for example, one of them doesn't aim correctly?
Well, the great thing about the Webb telescope is with these independent mirrors is that we can handle so many different scenarios like that. For instance, if one of the mirrors either, let's say, a piece of debris hits it, or during its launch and ascent phase, some of the stresses were higher than predicted, and we had a problem that broke a mirror or an actuator behind the mirror, we could actually take that mirror essentially out of the image by making it very much out of focus with the rest of the telescope. And, if anyone's ever experienced having a floater in their eye or something like a scratch on your eye, you can realize how much you can see. And it is completely unaffected by that. So when something's not quite in sync with the rest of the primary mirror, there's different ways to take that impact out. Some of it's physically by moving the mirror out of its focus, and some of it's digitally by knowing that there's a imperfection that's going to be in each and every image that gets subtracted out digitally from those images.
Thank you. Maybe another social media question. For those of you that would like to actually have questions answered live on air with us, use the hashtag #UnfoldTheUniverse. So we'll be looking for hashtag #UnfoldTheUniverse to take your questions on social media. And so this actually kind of goes along with the second one. So Michael on Facebook asks, what protects the mirror from micrometeors and other fine space dust debris? I think the answer is... not much.
Nothing. What you see is what you get. The sun shield is facing the Earth and the sun. So not only does it protect it a little bit from a little bit of possibly dust or anything coming from the sun, but the heat of the sun is basically what it does. If the sun shield itself, this isn't quite the question he asked, but if the sun shield itself got hit by a micrometeoroid and got a little tear or a rip in it, that's part of why we have 5 layers, and we can tolerate so much damage throughout time, and that was part of our lifetime calculations to make sure, based on our little bit of knowledge that we have of other observatories at the L2 point, to make sure that the environment there can be sustained by all of our optics and all of our sun shield over the time span that we expect to be there.
And just to give you an update, you're looking at live commissioning of the James Webb Space Telescope. From what I understand, there will be a call in about 4 minutes releasing the larger mechanism, and then about 4 minutes after that, we should be able to see the wing start to move. So now in a bit under 10 minutes, we'll see the wing move.
Yeah, the first release.
At this time, we're ready to continue with 693.034 DEU to operate frame 6.
Copy. What they'll do is...
Command line looks good. You are good to execute.
Copy. To see how to go to executing.
And you're good to continue.
Copy. Go to continue. To see how to go.
When they do the small move, this will verify for sure and for certain that all of those launch release mechanisms have released and that the mirror is free to move into its final position.
Right. Continuing our conversation, I mean, some small impacts from micrometeorites will happen. Over the lifetime of the mission, there will be some damage to the mirrors of the telescope. I remember at the Goddard Space Flight Center, when they replaced some of the cameras on the Hubble Space Telescope, they brought some of the old cameras back for analysis.
And can confirm operation frame 6, and we're ready to continue with the small motor move. So we're ready to go at 693.039.
Copy. This on the window.
That command line looks good. You're good to execute.
Copy that. To see you have to go to execute. Executing.
And you're good to continue.
Copy. Copy go to continue. To see how to go to continue. Copy go.
And stand by while we review parameters.
Copy that. Send him.
So we were talking about the debris. Also, being at L2 is very
I see
useful.
the parameters look good. You're go to move the motor.
Copy that. To see how to go to move. Copy go. And pro complete.
DevOps copies, and you can queue up the stop.
Copy that.
And the motor status is moving.
Copy.
See, got it. I remember the cameras being brought back for analysis. They were analyzing every tiny little crater that was made by a little piece of dust or a little piece of debris. So, but you said that L2, for example, is actually a very nice place to be. It's actually a kind of a cleaner place when it comes to space junk. Is that correct?
Yes. Low Earth orbit Hubble is in has a lot of space debris, as everybody has seen. I think it's gravity.
And I see you are go to execute stop deploy.
Copy that. To see how to go to execute. Execute.
And you're going to continue.
So
Copy go to continue. To see how to go. Copy go.
they're stopping the motor move now.
And I see the motor is stopped. At this time, we're ready to continue with 693.041 DEU to standby. Prompt looks good. You are go to execute.
Roger. See how to go to execute. Execute.
And you're going to continue.
We go to continue. To see how to go. Copy go.
Once they've taken a moment to analyze their telemetry and then move on again with the mirror moves, they're going to take the motor and they're going to drive the mirror up against a hard stop. Once they move it up against the hard stop and they verify that they're happy with that position, then they're going to start moving some latches into position. But when they move the latches into position, they'll kind of back off on that deployment motor a little bit to make sure that the latches are the ones that...
DevOps can confirm standby round robin. At this time, we're ready to continue with 693.042 to restore the gain stat parameter to default. That command line looks good. You are good to continue.
Roger, sir. To see how to go to continue. Execute.
At this point, they're just
continue.
Copy go. To see how to go. Copy go.
sending some configuration commands to the motors.
So once again, you're joining us for the live commissioning of the James Webb Space Telescope. The starboard wing of the primary mirror is being deployed today. In just a few minutes, we should be able to actually see it moving. On the left-hand side of your screen is a real-time visualization based on telemetry, based on data from the telescope. It's generated by a computer. This is not a camera. We do not have cameras, unfortunately, on board Webb, but this will show us the configuration that's actually in real time. And in just a few minutes from now, we will begin actually bringing that side part of the primary mirror around to form one large mirror of 18 segments. Segments that you see are colored gold. We'll talk more about the mirrors after we do this deployment. We'll have some time as the telescope is latched into its final configuration. But that is actual gold, very, very thin coating of gold, just a few hundred atoms thick. And telescope would actually look quite a bit darker than you see in that animation. The sun shield is blocking out all of the light from the sun and any reflected light from the Earth and the Moon. And so those mirrors right now are exposed to the dark, cold space that will be doing its primary science, looking out into the universe. I understand the call to move is imminent any moment now. And when the mirror begins to move, we will just all sit back together and enjoy watching that. And we'll come back with commentary after that has completed. And we have some time as they latch telescope, a couple of hours into its final configuration. So we'll have different guests and experts to talk about what's going on when that happens. I'm joined by Julie Van Kampen, and she is the Deputy Observatory Commissioning Engineer.
RTCP is complete. And DevOps copies. It looks like that load completed successfully. We're ready to continue at 693.043. DEU to operate frame 6.
Copy that. On the window.
And the command line looks good. You're good to execute.
Roger that. Did he go ahead and execute? Executing.
So they've just put the
And you're
mirror
good to
back.
continue.
Right.
Copy that to continue.
The deployment motor back into its operational state. It was taken out of operational state to do a reconfiguration. And now it's ready to do the full move once this is done.
We're coming to you live from the Space Telescope Science Institute in Baltimore, Maryland. This is happening in real time. The James Webb Space Telescope commissioning, the final wing of the primary mirror. You're looking at live coverage from the Mission Operations Center, the MOC. Command to deploy the wing is imminent. We're waiting for it any minute now, and then we will watch on the observatory visualization tool to see that. It'll just be a couple of minutes, something like 4 to 5 minutes, and then after that we will come back with more commentary about the observatory, and we'll talk to some of the people that are some of the science leads as well about some of the scientific questions this observatory has been designed to answer.
They've just given the
Stand by
command
while we
to
review
go
the
ahead.
parameters.
Okay, standing by.
They're reviewing the parameters to move
Okay,
the
I
mirrors.
see those parameters look good. You are good to move the motor.
Copy go to move to see how to move. Copy that.
And this will move the mirrors into their final position.
Complete.
The screen to the right shows us our ground station.
And the motor status is moving.
You can see the mirrors move in the visualization tool. It will take about 4 minutes for them to completely come forward.
And a reminder, this is real live footage. There's a 3-second time delay. It takes that long for light to travel at 186,000 miles per second. The James Webb Space Telescope is now well over 600,000 miles away.
And
Thing you remember about this?
Go ahead.
I was just going to say, just remember that this visualization is real. This is not pre-recorded. It's based on actual data coming to us from the telescope, being downloaded right now.
And the important thing about the light delay is not that the light takes that long, but the data, which moves at the speed of light, takes that long to come to us. I know that was a question we had on some of our social media before.
With the status, we have started our deployment into the deployed hard stops, and our current looks really good, nice and low.
Mount copy.
That was another of our deployment engineers confirming that everything looks good with our mission operations manager.
It's exciting to actually see it moving. You know, there it is on the visualization tool. It's getting closer and closer.
Yep, it's going to be momentous when it finally comes into position.
The first wing was successfully deployed yesterday, and now this is the final part, the primary mirror being put into place. Julie, give us a sense of the scale. These mirror segments, I mean, I had the honor of watching this being built, a lot of it at Goddard. How big across, for example, is one of those hexagons?
They're about 1.5 meters across from tip to tip. The hexagons are quite large. It's amazing to actually be in the clean room and look up to see the whole mirror assembled, towering above you. There's no amount of seeing it on photos that kind of gives you the sense of actually standing next to it in our clean room when it was assembled. And as we talked about before, and once it's fully into position here, the final shape that our primary mirror is going to be called a tricontagon. It's about a polygon.
Step lead on ops for about 3/4 of the way through the deployment, and everything still looks really good.
And the mirror itself will be concave. You can sort of just see that in this simulation. They actually have simulated some stars and things in space that you can see moving on the surface of the mirror. Also, as the mirror comes forward, and I'm not sure that we can see it at this angle, but there's a thing called the bat wing, and it's a shade that falls down behind the mirror to help shade any light or heat that might be coming up through the hole in the sunshade from keeping any of the backside of the telescope warm. There's one on each side that comes down passively as the motor moves this forward. And then the gaps between the mirrors are very small. I think it's on the order of several millimeters.
Step lead on ops. We have reached the end of deployment, and we are preloading into the latch pad.
All right.
You see people clapping? Yes. Wonderful.
Everyone's up on their feet, clapping.
Wow, just look at that. The primary mirror is successfully deployed. This is a first. We have made a space observatory the mirror was so large that it had to be folded up to fit inside the room.
OC, at this time we're ready to continue with 693.046. Enable activate SCS 256. And that command line looks good. You're good to execute.
Copy that. See, go ahead and execute. Execute.
I think you can hear the relief in our deployment ops.
And you're good to enable activate.
Copy, go to next.
Voice.
I have to say, I just feel this kind of glow, in my chest right now. Just seeing that mirror all deployed, all together. The size of a mirror allows us to collect more light from fainter objects, and in a lot of cases that means farther away objects that light took many billions of years to travel to us. A chance to see the universe as it was, perhaps only a couple 100 million years after the start, after the Big Bang. The sensitivity of this mirror will allow that. And the size of the mirror also gives us a clearer, higher resolution, able to see more detail in space than ever before. So this was something that absolutely had to happen. We had to unfold this mirror. The secondary focusing mirror had to come out, and then a little bit more than a week ago, the amazing sun shield, and there it is in front of us. You're looking at this animation. This is not a pre-made animation. This is based on actual data coming from the telescope to us right now. We are live at the Space Telescope Science Institute, and we have successfully unfolded the last part of the primary mirror. After this, are still more commissioning acts to come, very important ones, for example, focusing.
Okay, DevOps can confirm that 256 is active in the delayed state, and I've confirmed with the dep lead they're ready to begin the 3-door latch off stow and latch to safe. So we're ready to continue with 693.048, move 1 of 20.
Copy that. It's on the window.
And that proc looks good. You are going to execute.
Copy. This you have to go to execute. Executing.
You just heard
And
our
you're going to
deployment
continue.
lead
Copy, go to continue.
go through a mouthful of description there of what happens next. There's a hook latch, and it's basically really that. It looks like a big latch, like you would hook possibly on a bathroom door or a tie down. If you had tie down straps to hold some packaging onto the back of a vehicle, it's actually a hook. And you heard her call it 3-door, and what that means is it's essentially it has a couple of different degrees of motion that it can do.
Stand by for parameter review.
Copy that. Standing by.
Each of the latches are a little different in which degrees of freedom that they can move in. And so the 3-door
And
is
the parameters look good. You're going to continue with the motor move.
Copy, go. You see you have to go to continue.
is one of the types that we have.
This latching procedure will take a couple of hours. We will be here through the entirety of it. We will be able to tell you when it is complete. And we may pause our commentary now and again, but we'll have different guests talking about aspects of the engineering and science of the James Webb Space Telescope through the next few hours. And this procedure will take quite a while. Can you tell us a little bit more about the latching, what we're going to be witnessing in the next few hours, Julie?
Sure. There's actually several latches. The next one that you'll hear her talk about will be one of the 2 doors, and there's 4 in total, I believe, and each of these will come into position, and then they'll very slowly. They want to make sure that they don't do something that's called like over constrained. And as anyone who understands how a mechanism might move, you can easily kind of get yourself jammed into a position if you try to tighten one thing before you're completely aligned with another. Almost like when you change your tire, you want to kind of do that star pattern to wiggle it into just the right position to make sure it's flat. You don't want to tighten one of those bolts before you get the others snug, and you want to tighten them up in a pattern. So they'll do the same thing with these latches. They'll make sure that they're done in a very precise order, that the different degrees of freedoms of each of the latches are coming into play in the order that they had planned, to make sure that they get that mirror latched in and locked down in the absolute best position, so that those mirrors are in range for what they need to do for actually defining the surface of that mirror with the actuators and motions that will come next in the next couple weeks.
Well, Julie, thank you so much for being with us through this procedure. We're going to come back to you later on as this happens. At the moment, we are going to have one of our expert guests come up. We're going to be joined by
that motor move looks good. We are ready to continue with 693.049, 3-door latch to safe, move 2 of 20. And the command
Thank you for having me.
you're going to execute.
Copy that. Go ahead and execute. Executing.
Thank you for having me.
And you're going to continue.
And we'll come back to you later.
So you have to go.
Absolutely.
Happy go.
The the next person we're going to be talking to is the Associate Administrator for Science at NASA, Dr. Thomas Zurbuchen. Thomas, it is wonderful to see you. How are you feeling? Tell me about what you just observed.
Oh, I'm emotional about it. What an amazing milestone. We see that beautiful pattern up there in the sky now, almost complete. Of course, it needs to latch, but what an amazing milestone just ahead of it. 178 out of 178 of these, actuators that had to fire the right way. I'm just so amazed and in awe about this team.
So one of the things that I'm just sort of, I haven't seen you for a while without a mask. They have us all in isolated rooms, and you're always clean shaven. You look a little bit different today. Is there is there some story behind that?
You notice, right? So basically what happened is after we launched, frankly, I told my wife, I'm not going to shave until this entire telescope is fully deployed. This is like my favorite sports team when they're in the playoffs, right? You have to be sure that you fully support them. So that's what I'm doing here. I can't wait to shave. Michelle, my wife says, are they done soon?
And so, that actually gives us a chance to talk a bit about what's coming up next. So, about how long do you think it's going to be until you shave?
Well, I fully expect, assuming that everything goes well today, I fully expect to shave today. And I just want you to know, this team is basically on track within a half a day or so of the fastest schedule that we had outlined. Frankly, I sat there today with some of the managers and said, if you ask somebody, 2 months ago, even a month ago, hey, we're going to be done on the 8th of January. What would you have said? I said it's massively optimistic and unrealistic. I think this team is just incredible. Back to my sports analogy, we're seeing that the team on the playing field, and it's just an awesome team. And frankly, kind of over and above all expectations that anybody might have had.
Well, you're talking about the team, it all coming together, but then there are also some tremendous challenges that this team has faced. And, I know that that's something that you've been there with the team for quite a while now. Can you give us a sense about, not only did we have COVID, where we were all trying to do this and be isolated and be careful for each other's safety and all that, but there were all kinds of other challenges. Tell us about some of the things that, in your years on this mission, you were like, wow, I'm amazed they overcame that.
Look, I just want to tell you first, Michelle, I'm very humbled to be part of this team right now. And I know so many others were a part of this team for decades before I even showed up. I've only been part of this team for 5 years, and I'm honored to be part of the team. Yes, we've had a number of challenges. If you, of course, look at everything that, go backwards, anything with the deployments, some of the challenges, frankly, that the team immediately addressed, they made it look easy, even though some of these challenges, frankly, were tough. You go back in time, and of course, it's very hard to think about the grit of this team that we're seeing without thinking of COVID, right? What's really amazing is how they overcame that, right? How they did not, they took every excuse they could to stay on track, right? It's so often, Michelle, sometimes we see teams, in our private lives or even, elsewhere where all of a sudden, people take excuses to not fulfill goals. This team found every excuse to do so. You go back in time and you realize, how hard it is to be truly a single team. And Michelle, it's not just the engineers; it's the good people on Capitol Hill who are allocating the budgets, the people in the White House, all the stakeholders there. And I think what Greg Robinson, for me, it's just really important to say that name on what he managed to do and kind of overcame is really building a team from the top all the way to the technician, the single team. And of course, that's why it's going so well, right? Because of, unified teams, are a beautiful thing to watch.
This is the definitely not ops with the status. We're a couple minutes into our move to the safe position on the 3-door latch. Everything looks really good. The strains are low, and the strain offset came in right where we wanted it. So we're looking good.
Mom copies that Boston Dep Lead. Keep going.
So as the Associate Administrator for Science at NASA, you are a scientist, and there's some incredible scientific goals with this mission. And like we said, that this all started from questions. We launched the Hubble Space Telescope. We understood there was so many more things to see, even farther back in time. Give me a sense about some of the science that you're most looking forward to. Hopefully, that this mission will accomplish.
How much time do you have, Michelle? Right, I'm going to give you like a couple. But I've been doing a lot of reading and thinking about this kind of early universe and the galaxies, and for me, the potential impact of primordial black holes in this whole discussion, really the relationship of galaxies and black holes that are so tight. As we look at today's galaxies, kind of in our neighborhood, like how did that go there? For me, it just boggles my mind, to think of these enormous structures in the universe that are in the past. I'm going to give you a second example, Michelle, and of course, it's about finding life elsewhere, but I'm going to focus on our own solar system. We're going to make observations, for example, of Europa. We did that with Hubble, and there's amazing papers out there from Nature and Science that says, just marginally, we can see kind of emissions of Europa that kind of are similar to Enceladus, for example, where water from these subsurface oceans is coming out together with organics at Enceladus. The question is, does that happen with Europa? And of course, we're moving towards a launch of Clipper in 2024, and we want to make sure that if there are such emission points, that we know that, because we want to take the measurements with that amazing mass spectrometer on Clipper. There's similar type of discussions on Mars, where of course we're in the middle of another huge adventure trying to get these samples back in the first round trip to another planet. And for me, again, observations of the Martian atmosphere, its composition and its dust components are just so critical.
This is something that I think that, I've really enjoyed seeing your leadership on in the last years is no mission stands alone. We have missions, each one supports the other. It's not just this mission, then that one. There's a strategy that everything works together. So like you said, for exploring the solar system, you have something like the Webb telescope, which from a distance can see things like Mars, Europa, places like Titan. But then we have missions that are poised to go there and explore closer up as well.
Oh, I strongly believe that, right? What's so beautiful about nature and so amazing about the science program we have at NASA is the interconnectedness between the different questions that are there. And to me, that has always been one of the most exciting parts of studying nature, is to see relationships that were not innately recognized there. And I think the more we learn about nature, and especially in astrophysics, the more we see some of these connections, right? I'm always in awe. I read some papers, not as many as I would like to, Michelle, but nonetheless, I read some of the papers. I realize that atmospheric models of exoplanets so often are done by our good people in Earth science, because they know how to do
halfway through our
in ways that nobody else can. So yes, it will better all these missions, because nature is also
haven't changed significantly.
Absolutely. Listening to commands from the mock, making sure we stay up to date on them. But absolutely. I mean, you mentioned the first stars. And there's probably plenty of people in the audience that don't really know your background as a scientist. Maybe you can get a little sense about your scientific expertise and how you came to be Associate Administrator of NASA.
Well, so I studied astrophysics, and I was really inspired by some of these missions. Frankly, I remember when I was 8 years old, I got this book about the Voyager missions and some of these telescopes that Nancy Grace Roman, right? It really started imagining. That was in the 70s. When I got this book, and that inspired me out of the little mountain village in Switzerland to be where I am right now. I'm an astrophysicist, but I mostly focused my work about the sun and kind of the inner solar system. So I know how to do mass spectrometers, and I've worked with teams. And what I fell in love with, Michelle, is really the ability of working with amazing teams. When I see a team, whether it's in athletics, or whether I see it in this control room right there, team that is truly operating at their highest capability. I'm so excited to see it. It's the most beautiful thing, but I'm also, it gives me so much hope of all these other things we can do. So when I look at astrophysics, of course, I think of the classes and so many of the things that I learned in the late 90s that are no longer true. And that's what science is about, because we learn all the time. Can you imagine, even in 5 years from now, how classes everywhere around the world will be affected by this very amazing observatory that's being set up right now?
Yeah, there's going to be some very, very profound things. I mean, you were talking about looking at some of the first galaxies to form. And this, of course, is one of the reasons why we have an infrared telescope, which is different from Hubble, which was largely in visible light. Infrared actually allows us to see, to some extent, farther back in time, farther away in the universe, where the expansion of the universe has actually stretched out the light from visible light into the infrared wavelengths. And you mentioned this close relationship between black holes and galaxies. I mean, a lot of our viewers out there probably don't realize that we are orbiting around a giant black hole right now at about 500,000 miles an hour, the giant black hole in the middle of the center of the galaxy. And there seems to be some relationship between how galaxies form and how black holes form. But there's a real mystery about these big black holes that we see so far away and therefore so far back in time. Maybe give us a little more sense about, this is one of the things that as an astrophysicist, we look at and we say, I don't understand how that happened.
Right, it's truly a chicken and egg problem, right? Kind of right now, it seems to be the case that black holes and galaxies really coexist, right? It's actually really hard to find a galaxy in which there's no black hole there. It really seems that it's a really important part of the galactic evolution. But how does that start? Is the black hole first? What is the role of the black holes? From the beginning, you talked about the interconnectedness, Michelle. We're right now setting up a small telescope we launched a few weeks ago. IXPE, the Polarimetry Explorer, and hopefully next week we'll be able to give kind of first light of that kind of X-ray observation, kind of again providing new insights about some of these kind of more recent black holes, kind of really trying to understand what the mechanisms really are, and that in those black holes, but also the environment around it. For example, the roles of magnetic fields that are so critical in so many of these areas.
I know for me, one of the things is when you're looking at the universe, in the case of Hubble, we've been able to see black holes that are gigantic. They are millions of times the mass of the sun. And we're seeing them at a time when the universe was only, say, 500 million years old. And black holes, we tend to think of as being formed by stars that die. But, when you think about the universe being that young, how did such a huge black hole form that quickly? And as an astrophysicist myself that studies stars, one of the things that I'm hoping Webb will shed some light on is the fact that the very first stars in the universe might have been quite different than the stars today. And maybe that's something you can give us a little bit of an idea. Why would the first stars be that much different from the stars we see around us right now?
I think it's a really great question, and I think it's one of the most amazing parts of really talking about how we relate to our universe. And that is that, of course, when the universe starts at the beginning, the atoms that form really are much less rich in terms of diversity than we have today. On my hands, I have gold and platinum rings that my wife gave me, and we know that those are not from the beginning of the universe. Frankly, they come from neutron stars that are merging, that are much, much later, after a lifetime of a star. So when you look at the first stars, like what you have, kind of the material you build with is much lighter than stars that are that most of the stars that we're looking at night through a telescope, because those stars are next generation stars in so many of the cases with much heavier components that are there. So the question really is, how do you build those first stars? And frankly, how do they then kick off that evolutionary process? There's a lot of models. And the data will, of course, constrain these models. That's what we call learning, right? It's saying this model is correct, this model is not correct. And by the way, there's an observation that none of the models predicts, which is the element of surprise. We can always bet on the element of surprise, Michelle. Frankly, often the surprising parts are the most important ones.
I sort of like that. We're talking about the history of chemical elements, but in there is always the element of surprise. Yes, the universe began, with hydrogen and helium, a tiny little bit of a couple other elements. But as you mentioned, everything that really makes us up, things that make up a human body, like carbon or the calcium in our teeth, or phosphorus or sulfur, the things that we need for our DNA.
We have completed this move of the 3-door latch to safe. So we're going to proceed with the 2-door latch.
One of the things that we're really hoping that the James Webb Observatory will shed some light on is what the universe was like before most of that formed. I mean, really the origins of the stuff that we are coming from. But there's another part of our origins too. You mentioned, in 5 years' time,
ready to begin the 2-door latch off stow. That is motor move 3 of 20. The command line looks good. You're go to execute.
Copy that. CC, go ahead and execute. Executing.
And you're go to continue.
Copy go. CC, you have to go to continue.
One of the things that I'm really looking forward to is being able to maybe in a few years from now point to a star up in the sky and say that there's a planet around that star that has an environment similar to us here on Earth. Maybe to take us through how will Webb do that? How will Webb be able to explore what the actual environments on planets that far away around other stars? How will Webb be able to do that?
So if you go back in time of the Earth, of course, long before we were here, the atmosphere of our planet was very different. And frankly, the emergence of life on the atmosphere here, kind of in that Goldilocks zone, right, where water can cool, the emergence of life really changed the atmosphere. Frankly, there's a number of papers out there that said a large fraction of the nitrogen in our atmosphere may very well be from the emergence of life. There's other, of course, elements, oxygen type of, ozone, elements like that really come, of course, are very much part of that cycle of life that is here. So as we look at other planetary atmospheres, right, the question really is, what are the patterns there? And can we find patterns that are indicative of the presence, both the ability to have life there, but even in some cases, kind of the follow-up or kind of the consistency with life there. Certainly from what we've learned here, but perhaps also other versions that we yet have to we have to learn. Of course, what's so hard about life is we have n equals 1. We know only one life. All life on Earth is related, and we learned a lot when we went from one solar system to many solar systems, stellar systems. Frankly, many of the models crumbled within weeks of the first observations that were published in 1995. So when we look at life, I'm sure similar things will happen. But for me, that's why that's so exciting, Michelle.
Well, that's absolutely wonderful. So once again, we're speaking to Dr. Thomas Zurbuchen. He's the Associate Administrator for Science at NASA. Thomas and our audience out there, we're going to take a short break. We're going to take a pause in the commentary, and we will be coming back at 11 o'clock in the morning Eastern Standard Time to resume our commentary. But Thomas, thank you so much for joining us. What an exciting day, as you said, very emotional. And I'm just so pleased to be able to be here on the floor beneath you. So I'll wave to you from down in the building.
Yeah, just really want to thank you for all the amazing work you've been doing, Michelle. It's been wonderful. I've watched you many times from different locations. I know you have exactly the same passion I do about this amazing science, and you can't wait to get those data back in just a few months' time.
Absolutely. Thank you so much for joining us, and we'll be back in our commentary in just a few minutes.
Thank you. Yeah.
Okay, and OC, that motor move completed successfully. We're ready to continue at 693.052. 2-door latch to safe, move 420.
Roger that. That is on the way.
And that command line looks good. You're go to execute.
Copy. Go ahead and execute. Execute.
And you're go to continue.
Copy go. You have the go to continue.
And stand by while we review the parameters.
Hold please, standing by.
OC, the parameters look good. You're go to continue with the move.
Copy, go to continue. CT, you have to go. Ready.
ढोंगी साधु तूने दवाई के बारे में मोबाइल ले लिया जो कोई कहेगा कि चपाटी मार के तुमने लात मार के बताता हूँ तू दवाई के बारे में मोबाइल ले लिया छोड़ी मत क्या मरे हो
To see the motor move is in progress. It will take about 14 minutes.
Copy, 14 minutes. Well, stand by.
मैं रोज बात करना चाहता हूँ बता के जल्दी टाइम पे ये तू वेब चल रहा है ना तो मैं आपको क्या पाना वो गेम खेलेगा नहीं मुझे रोज बात करने के लिए मेरा मोबाइल दे दे कितना टाइम देगा 10 मिनट अभी नहीं देगा तो देखते हैं अगला 800 डॉलर
Definitely not ops with the status. We are on step 4 of 20 of latching. We're latching the 2-door to the safe position into it a couple of minutes now. Again, the strains look really good, nice and low, and our strain offset is matched our predict, so no updates required there.
Excellent, Mom. Copies. Thank you.
This is Oceans.
This is Dep Lead on Ops. We are halfway through this latching to the safe position on the two-door, and everything still looks really good.
Welcome back to our live commentary.
Posty copies.
If you're joining us right now, you are looking at live coverage of the commissioning of the James Webb Space Telescope. I'm here at the Space Telescope Science Institute in Baltimore, Maryland. And what you're seeing on the screen above me is a live footage from the mock Mission Operations Center for the James Webb Space Telescope. And then to my left is an observatory visualization tool, which is showing you real-time data, telemetry, as they say, from the James Webb Space Telescope, which is now over 600,000 miles away from us, on its way out to an orbit about 1 million miles away, past the moon, L2, the Lagrange point. And just a few minutes ago, we successfully deployed the final part of the primary mirror, the side wing. So this has been a wonderful morning so far here in Baltimore. We still have a few hours as they latch this primary mirror segment in place.
हाँ खाना बन गया क्या? अभी तो पहले वहाँ पे दिख रही हो। हाँ। आ रहा और
This is Step Lead on Ops with the status. We've just completed the two-door move to safe position. So now we're in a position to stop the deployment motor and recenter it.
Copy.
OC, this is Step Ops on Ops. So per Dep Lead, that motor move completed successfully. We are going to continue at 693.054 to terminate SCS 256.
Copy that.
That command line looks good. You're going to execute.
Copy. CC have the go to execute. Executing.
You're going to terminate.
Copy, go to terminate. You have the go to project.
And OC, this is Step ops, you are go to disable OCSID 256, step 55. The command line looks good, you're good to execute.
Copy that. See how to go to execute. Executing.
And you're go to disable.
Copy that to disable.
Roger.
RTCP is complete. Copy.
Okay, and OC, you are go to execute the DEU stop deploy at 5-6. That command line looks good, you're good to execute.
Copy that. CC how to go to execute. Executing.
And you're good to continue.
Copy go to continue.
Roger.
RTCP is complete.
Okay, OC DevOps can confirm that the motor is stopped. We're ready for 693.057 DEU to standby. And the command line looks good, you're good to execute.
Copy that. CC how to go to execute. Executing.
You're good to continue.
Copy go to continue.
Roger. The DevOps can confirm standby round robin. OC, we're ready for step 693.058 to raise the integral gain.
Copy that. On the window.
And that proc looks good, you're good to execute.
Copy. CC how to go to execute. Executing.
You're good to continue.
Copy go to continue.
Roger.
Time we'll have some chance to recap some of the story of the James Webb Space Telescope, as well as talk to some of the expert scientists and engineers that are working on that. So if you're just joining us, you can also talk to us on social media. We ask that you use the hashtag #UnfoldTheUniverse. So hashtag #UnfoldTheUniverse, and we'll get to as many of those questions as possible. So this has really been a momentous day. Everybody is very happy with how things have proceeded. I think that it's a really nice chance to kind of go back and talk a bit about the larger story of how the James Webb Space Telescope got to where it is today, over 600,000 miles out in space, headed toward a Lagrange point, a balance between the sun and the Earth's gravity, where it will hopefully have many years ahead of it observing the early universe, exoplanets, and all things like that. So this telescope has actually been in development for many, many years. A lot of people say that 1995 was the time when it began, when we started planning for this observatory. And what you're seeing now is some footage of actually putting together the primary mirror. Much of this work, building the primary mirror and the observatory and testing it, was done at Goddard Space Flight Center. These are acoustic and vibration tests, which were necessary to make sure the telescope could withstand the pressures of launch. So there's our acoustic test chamber, and you can see there the telescope is wrapped to keep it clean. This is a vacuum test that was done at Johnson Space Center in Houston. This is what we call Chamber A. This is the largest vacuum chamber that NASA has, and this was made during the Apollo era. It was actually large enough to fit full command modules of the Apollo mission in there to test. So what you're seeing now on the screen in front of you right now is live footage from the MOC, the Mission Operations Center. That's right above me as I'm speaking to you. And to the left is our observatory visualization tool. This is a computer-generated image, but this is a live image generated by data that's actually coming from the telescope as we speak. So what happened just a few minutes ago was the starboard side of the primary mirror, the mirror wing, was released into place. And that's an incredible accomplishment. The mirror is now fully unfolded, and that's for all of us here.
We're ready to continue with 693.059
incredible relief and some incredible joy.
Command line looks good. You're good to execute.
Right on that.
You'll see.
Go ahead and execute. Executing.
You'll hear me pause as I listen to what's happening in the control room. They are just making sure that all the different lenses are firing successfully.
Roger that.
And as I mentioned, this procedure will go on for a couple more hours. We will stay with it through the entire thing so that at the end we'll be able to tell you that the mirror has been safely latched into its final position. And that will mark the end of some major commissioning efforts of the James Webb Space Telescope. There is more to come. This is not the last phase. After this, we will be focusing the primary mirror, which is made of 18 independent segments. And then there will begin commissioning of the science instruments as well. So I think right now it's also a chance to sort of talk about the journey that Webb has been on. This is a portable, clean room. The Webb telescope, of course, had to be kept under very, very clean circumstances. And that left California on a special ship that is actually designed to take a lot of these specialized spacecraft cargo to the launch site that the European Space Agency runs in Kourou, French Guiana. This is in South America. And here you're seeing footage of that portable clean room with the Webb Observatory inside being taken off the ship and being loaded onto the place where it will go up on an Ariane 5 rocket. So that's part of the journey of Webb. And here you see actually opening up that portable clean room. Webb is in its stowed configuration, folded up. This is one of the reasons it's been so exciting the last couple of days. This observatory, for the first time, we've launched an observatory that was so big, the mirror had to be folded up. And as people often compared it to Oregon, we folded up the telescope so it could fit inside the fairing of the Ariane 5 rocket.
Yeah, bye.
Once again, moments ago, we saw the final part of that major commissioning of unfolding the mirror happen.
And OC, you are going to continue to move the motor.
OC copy. CC, how's it go?
As they continue the latching procedure, one of the things we can also look back on is the launch. This was a Christmas present for all of us. This was about 7:30 in the morning Eastern Standard Time in the United States. And there you see the launch of the Ariane 5 rocket. It was an absolutely perfect launch. They were able to get enough energy from the launch itself to save some of the fuel on the Webb telescope, which we hope will extend its life. And here you see some of the people at Mission Control in French Guiana cheering after the successful launch. And what you're looking at here is an animation of the observatory going away from the rocket. This is not an animation. This one here is the actual footage. There was a camera on the rocket itself, and here we see the Webb telescope coming off the Ariane 5 second stage on its way out to the Lagrange point, L2. That's about 1 million miles away from Earth. It's on the other side of the moon. It's a wonderful environment for an infrared telescope that needs to be very cold. Here you're actually seeing, again, this is real footage from the camera. You're seeing the solar panels unfold. This was the very first of the actual unfoldings that had to occur because now the telescope was able to power itself up using radiation from the sun. And then after that, of course, came the amazing There's everybody celebrating. People, of course, put in huge amounts of time. They were here over the holidays. All of us have been working straight through Christmas and New Year's, of course. It's been wonderfully joyful, but there are a lot of families back at home that I'm sure missed us as well. Here's an animation of some of the major commissioning points that we've actually accomplished. So the solar array was unfurled, and also the antenna that allows the Webb to communicate with the Earth. Now you see the Webb moving up from the sun shield, which is now beginning to unfold. This is a 5-layer Kapton sun shield. It's a material that's very much like mylar. It's a very thin, very strong material. In this case, it actually has some silicon in it to make it more reflective, and also put together in small segments so that it's very strong and can withstand any sort of small impacts from micrometeorites, which we do expect over the course of the mission. And now that incredible sun shield is fully extended. The secondary mirror came out a few days ago. Yesterday, we saw the first of the wings of the secondary mirror extended, and today we're just completing the second part. So now that we've gone through a little bit of an update as to what this tremendous journey that this observatory has been on, it's my pleasure to talk to Lee Feinberg, who is one of the senior engineers on the Webb telescope, and he's going to talk to us a bit more about some of these mirrors and some of the technology in Webb. So for one thing, Lee, wonderful to see you. We're all isolated from each other so that we can speak without masks. I'm downstairs.
Stopped at the spot he wanted to stop at.
Hi, Michelle.
We are ready to continue to begin the 3-door cup latch to capture move.
So as we said,
and that is move 520. The command line looks good. You are good to execute.
So in our conversation, you'll probably hear me pause just when I see the mirror distance.
Executing.
Lee, where you're sitting, can you hear those calls from the mock?
I'm sorry, can you say that again, Michelle?
Where you're sitting, can you hear those calls from the mock?
I can hear them, yes.
Okay, right, excellent. So for one thing, but before we launch right into the technical, tell me a bit about how you're feeling right now. We're human beings first.
Yeah, well, I feel good. I feel like the mechanical and the deployment teams really have done a phenomenal job. The optical team actually is just about to get started, so it's sort of a transition time. But to see a full primary mirror, this is something we've really been thinking about for a long time, and it's just a great thing to see and to be ready to start aligning those mirrors.
Absolutely. Well, let's talk a bit about those mirrors. I mean, that's sort of the expertise that you bring with us. So to begin with, these are very different mirrors than most people are used to in their regular life, in many, many ways. Obviously, incredibly specialized. Tell us about some of the ways these mirrors are just completely unique and very different.
Yeah, well, let me start by just saying, when we started this a couple decades ago, we knew from the very beginning that one of the hardest parts of making the observatory was going to be the mirrors. And in fact, if you go all the way back to the first project manager, Bernie Siri, he used to have this chart that would show that, one of the key goals was to make a mirror that could be lighter than the Hubble mirror by about 10 times per unit area. And it had to work at incredibly cold temperatures, minus 400 degrees Fahrenheit. And it had to have a quality of the mirror that was approaching the quality of visible mirrors, like the Hubble Space Telescope kind of image quality. And so these were, a set of challenges that were extremely difficult. There were some people who thought we couldn't even make mirrors that were this light and this quality. So actually it was a pretty collaborative effort. We actually worked with 8 other government agencies, including the Department of Defense. It was a collaboration to invest in multiple different mirror technologies, one of which was actually a technology in which the mirror has a bed of nails under it, a whole series of little tiny actuators. But one of them was a beryllium mirror. And the beryllium that was developed for Webb, it was actually a new form of beryllium. They called it an optical grade beryllium. And it was developed by a company that was called Brush-Wellman that then later became Materion. But this optical grade beryllium was supposed to be more uniform and was going to have better properties for being a telescope. And the key, though, was could you build large mirrors that are about almost 1.3, 1.4 meters in diameter? These are segments that are incredibly lightweight. So you have to be able to machine the mirrors from the back to lightweight them. And so it was a several-year technology development. It really took groups from all over the United States. The machining was done in Alabama, and the polishing was done in California. And here actually you can see some of the beryllium billets that were made in Ohio. So we developed the technology, and there was a mirror that was almost the full size of what the ultimate segments look like. We called it a prototype mirror. And here you can see the light weighting of the mirror from the back. And so that was the first phase, was just making a single mirror that could meet our requirements, including a gold coating that would reflect the infrared light. And so it was a large team effort. Ball Aerospace in Boulder, Colorado kind of led that team. And that mirror actually was competing with other mirrors. We had a very intense process by which we selected which mirror technology we would use. But beryllium won out because of its superior qualities at these very cold temperatures. And that's really the key. Beryllium has this amazing property that when you take it to these very cold temperatures, it's incredibly stable. There's a material property called coefficient of thermal expansion. And for beryllium, that material property is like as perfect as could be at these very cold temperatures. And that really was one of the key reasons we selected beryllium, along with the fact, one of the big benefits is it's extremely light. And if you look at how large the telescope is, 6.5 meter diameter, if we didn't make mirrors this light, we would not be able to lift them with a rocket. So it was a long effort. We then had to manufacture the mirrors, but that's what led to the mirrors.
The story actually goes, even farther back than that. So where was the beryllium mined? You were saying that this is sort of a new type of beryllium. But where did it start? Where did the beryllium actually come out of the ground?
Well, so it's actually mined in Utah, and it's mined in sort of these chunks and rocks that eventually will get ground up and eventually made into a powder form. And that was one of the things that they were able to do, was make a finer powder, a powder that has more spherical qualities. And then once you get that powder, and this was what Brush Wellman did in Ohio, just outside of Cleveland. Once you get that powder, you can actually do a process that's called hipping. It's hot isostatic pressure. It's a process that puts heat and pressure on the beryllium and forms a billet of beryllium, a block of beryllium, that we would slice like an Oreo cookie into two mirror blanks. And that's how we got sort of the large blanks that would make up what we would ultimately then machine. And so the first step was to go from Utah to Ohio, and then they would be sent to the Cullman, Alabama, where the machine shop was, that would lightweight the mirror. And they would also put on the front surface, they would literally machine a surface that was approximately the surface we needed for each mirror. But that was only the beginning, because the next phase was you had to grind and polish the mirror. And that, typically when you make a mirror, it's the polishing that's the hardest part. And actually the hardest part of that process is testing the mirror. And one of the key things we had to figure out was, how do you test mirrors that are inside of a cryogenic chamber? To the level that we needed. And nobody had done that before. And we also needed to make sure that all 18 mirrors matched each other. So that, if you made one mirror and then you made a second mirror, and you align them relative to each other, they need to have the same curvature. And that actually turned out to be one of the more difficult problems. So we had to develop methods, for testing mirrors and then for polishing the mirrors. When you cool a mirror down to minus 400 degrees Fahrenheit, it will literally deform because things shrink, but they shrink in a way that's not perfect. And so when we made these mirrors, what we did is we would put them inside of a chamber that would cool them down. We would test them with devices that are outside of the chamber. And once we knew how they deform, we would warm the mirror back up, send it back to the place that polished the mirror, and we would polish the inverse of the way they deformed. That process we call cryopolishing. And here you can actually see the mirrors going into the chamber. This is actually at the Marshall Space Flight Center. It's a chamber that was used for the Chandra Space Telescope, was converted for testing these mirrors. We put a special liquid helium shroud inside of it. And we also developed new test equipment that could work in the presence of all the vibration that we would get inside of a vacuum chamber. So we did all that work. We polished the mirrors with the inverse to deal with these cool down